In this video, we're going to try to figure out how to see what the graph of the original function f of x might be if we see what the graph of its derivative f prime of x is. So on this one, we're looking at the graph of f prime, and we can see that it's continuous. So if the derivative is continuous, then that means that the original function will have to be continuous as well. Now, part A, it's kind of hard to read here, but we're going to look for intervals where f is increasing. So f will be increasing when its derivative is positive. And so I've drawn in red there the interval where we can see f prime is above the x-axis. And even though it's 0 at -2 and it's also 0 at 1, if the derivative is positive on that open interval, then the original function is increasing on the closed interval. So for part A, we'll say that f is increasing on that interval that goes from -infinity to +1, and we'll include the +1. Part B says on what intervals is, and it's kind of hard to see here, but it should say is f concave up. So we're looking for where the function is concave up. The graph of the original function will be concave up when its second derivative is positive, and that's going to be where the derivative is increasing. So as we look at the graph of the derivative, we're looking for places where it is going to be increasing, and I've put those in blue. So for part B, we're going to say that f is concave up on that, and concavity is always going to be an open interval. So on that interval from -2 to 0, and also on the interval from 3 to 4. Part C says at which x-coordinates does f have local extrema. So we're looking for relative extrema here. And we're going to see from the derivative that the original function f will have a relative min when the derivative goes from negative to positive, and a relative max when the derivative goes from positive to negative. So if you look right here, you can see to the left, the derivative is above the x-axis, which is positive, and over here, the graph of the derivative is below the x-axis, which means it's going to be negative. So since it's going from positive to negative, that means we're going to have a relative maximum, and we don't know the y-coordinates. So we're going to say at x equals +1. Part D says, Part D says at what are the x-coordinates of all the inflection points of the graph of f. So here we're looking for what we'll call POIs, points of inflection. So we'll see an inflection point when the second derivative of f changes sign, and that's going to be where the graph of f changes from increasing to decreasing or decreasing to increasing. So we can see here the derivative goes from decreasing to increasing, and here from increasing to decreasing, and here again from decreasing to increasing. So as long as the original function is defined and continuous, relative mins and maxes in the derivative will correspond to inflection points in the original function. So we're going to say there's POIs at x equals, and that's going to be a -2 and 0 and +3. And then we're going to try to sketch a possible graph of f of x. Now, we don't know any y values, so we don't really know what the scale is here, but we'll see what we can do. So there will be many different possible correct versions of what the graph of f looks like. Let's see, we know we have a relative maximum at x equals 1, so I'm just going to arbitrarily choose the y-coordinate there to be the relative maximum. We don't have any relative minima. Now we can see that here at this point the function went from positive, then we had a 0 derivative, and then it went positive again. So that's going to be a place where we're going to get a shelf point. So it's going to increase, then go horizontal for a moment, and then continue to increase after that. So let's see, it's increasing everywhere to the left of 1. It's going to be, we have inflection points at -2 and also at 3. So we're increasing everywhere to the left. We're going to have an inflection point at -2. We're also going to have an inflection point at 0, and because it's going to change from concave up to concave down. And we're also going to have an inflection point at 3, somewhere in there. So let's see, to the left of -2, since it starts being concave up to the right of -2, it's going to be concave down and increasing. Then it's going to look like maybe we're going to have a relative max, but then it's going to turn around and start increasing again. So there's our shelf point. Then at 0, it's going to stop being concave up and start being concave down. We're going to hit that point at 1 where we have a relative maximum. Then it's going to start decreasing, but it's not going to be concave up again until we get to 3. So it's decreasing and concave down. Then once we get to 3, it's going to continue decreasing, but then be concave up until we get to 4. So something like that. Okay, let's see what we can do next. So I'll move this up a little bit. So we have, okay, so here we have a motion problem, and this is our position. We're moving just along the x-axis. And our position is given by x of t is 2t cubed minus 14t squared plus 22t minus 5. T is only going to be greater than or equal to 0. So the velocity is going to be the derivative of our position. And so that's going to be 6t to the second minus 28t plus 22. And our acceleration is going to be the derivative of velocity, which is the second derivative of position. I guess we call that x. And so that's going to be, let's see, 12t and then a minus 28. So they don't really give us much. They say describe the motion. So let's see what we can do with this. We can factor that 2 out, and that's going to be 3t squared minus 14t plus 11. Let's see if we can figure out where that's 0. And I think that actually factors. So we'll leave the 3 out, and I think we can get a 3t and a t, and I think we want the minus 11 here and the minus 1 there. That's going to give us our negative 14t middle term. So we're going to get t is 11/3 and t is 1. So if we do a number line for x prime, which is our velocity, and we're only going to go from 0 to forever, then 1 is going to be one place where the velocity is 0, and then 11/3, which is like 3 2/3, is going to be another place. So if you plug in a number less than 1, like say a half, then this is going to be a negative, and that's going to be a negative, and the product will be positive. And then if we plug something like say 2, then this will still be negative, but now this is changed to positive, so our velocity will be negative. And if you put in something bigger than 11/3, then these are both positive, and it's going to be positive. So what we get from a positive velocity is that the particle is going to be moving, since we're moving along the x-axis, it's going to be moving to the right. So that's going to tell us that our particle is moving to the right until we get to 0. At 0, we will say the particle is at rest. It's not moving right or left at all. Then on this time interval from 1 to 11/3, the particle is going to move left, and then it's going to be at rest again at 3 2/3, and then it's going to move right again for the rest of time. Now the acceleration, if we set that equal to 0, then we're going to get 12t equals 28. So t will be 28/12, which I think we can reduce by 2 and get 14. I guess we could do by 4 and get 7/3, which is like 2 1/3. So if we look at a number line anyway, again, we're only going to go from 0 to on the left. We'll cut it off at 0. So somewhere here at 7/3, like 2 1/3. So if you plug in something smaller than 2 1/3, like 2, it's going to be negative, and to the right, it's going to be positive. So this is now acceleration. So that means that it's the acceleration, what would we say? It is decelerating, or the acceleration is decreasing to the left of 2 1/3, and it's increasing to the right. So interestingly enough, the speed of that particle will increase when the velocity and acceleration are the same sign, and it will decrease, the speed will decrease when the acceleration and velocity are different in sign. So what that's saying is when we're starting out going to the right here, according to our velocity being positive, since the acceleration is negative, it's going to the right, but it's slowing down, which kind of makes sense because it's going to come to a complete stop at time 1, at t equals 1. Then it's going to change direction, and so now it's going to the left. And now at this point between t equals 1 and t equals 2/3, now the speed, the velocity and acceleration are the same sign, so it's moving to the left, but it's going faster and faster to the left until you get to 2 1/3. And so at 2 1/3, somewhere in here, now the velocity is still negative, but the acceleration is going to switch to positive. So it's moving left, but it's slowing down as it moves to the left until it comes to a complete standstill just briefly for a moment at 3 2/3 seconds. Then it changes direction again, so now it's going to the right, and because now the velocity and the acceleration are both positive, it's going faster and faster and faster to the right. Okay? Well, let's go on to the next panel and see what we can do. I guess we'll skip a couple of panels here. You can read through this. There's some good information. And there's some good information here as well. I'm going to go until we can get to a problem to do. Here we go. So now we're told here, this is again the graph of f prime. I'm going to blow that up a little bit. And so here we see a discontinuous f prime, but we're told that it's going to be a continuous function f. So our function here is still continuous. And we can see that we're going to find the x-coordinates of all local extrema and also points of inflection. So remember, relative mins and relative maxes are going to come where the derivative is 0 or undefined and where the derivative changes sign. So we can see, for example, right here at x equals -3, the derivative goes from positive to negative. So at x equals -3, we're going to have a relative maximum. At x equals -1, the derivative goes from negative to positive. So we're going to get a relative minimum at x equals -1. Now, At 0, you can see the derivative is undefined, but you can see it's undefined because the open circle's there. On the left side, the derivative is above the x-axis, is positive, and on the right side, the derivative is below the x-axis, so it's negative. So since the derivative changed from positive to negative, we're also going to get a relative maximum at x equals 0. In a similar fashion, we can see that the derivative is undefined here at x equals 2, and, oh, I skipped one. Let me back up. Here at x equals 1, the derivative goes from negative to positive, and so that's going to make that be another relative minimum. At x equals 2, the derivative is undefined, so that's a critical point, and it goes from positive to negative, and so that's going to be another relative maximum at x equals 2. So the places where we see these undefined derivatives, we can see that we have finite derivatives on either side, so it's not going to be a vertical tangent, nor will it be a cusp. Since the original function is continuous, that means these are going to have to be corner points. So those are going to represent corner points. Places where the derivative changes sign, but the function behaves very smoothly and continuously, that's going to be our kind of normal relative maximum or relative minimum. That's going to look kind of like a nice curve there. Okay, and we don't, so we have relative extreme. These are relative extrema. Now, inflection points are going to be where the function, the derivative changes from increasing to decreasing. So if we look for places where our derivative goes from here, it goes from decreasing to increasing. So at x equals negative 2, we're going to get an inflection point. And it also looks like it goes from, well, I guess here it goes from increasing, but then it's increased. I'm sorry. Yeah, it goes from increasing to the left here, but then it's increasing again there. So that's not going to be an inflection point. And here it goes from increasing to constant. So that's not going to be an inflection point either. So I think our only inflection point is going to be at x equals negative 2. And we don't know any y values, so we're going to have, we're going to get a shape of our f of x. We're going to try to come up with a graph of the shape of f of x, but we don't really know. There could be many different versions of this f of x that have different y values. So I think we'll try to plot at negative 3. We're going to have a relative maximum, so I'm going to choose that to be at that y value. At negative 1, we're going to get a relative minimum. I'm going to pick that to be there. At 0, we're going to get another relative maximum. I'm going to pick that to be here. At positive 1, we're going to get another relative minimum. I'm going to pick that y value to be there. And at 2, we're going to get another relative maximum. I'm going to pick that to be there. But the y values I'm choosing are just arbitrary. There's no particular reason for that. So let's see. To the left of negative 3, our curve is above the x-axis. So that's going to be increasing. And the derivative is decreasing, so it's going to be, well, let's get our inflection points. Our inflection point's at negative 2, and so in between the max and min, I'm going to say right there, I'm going to choose to make that an inflection point. Okay, so left of negative 3, our function is above the x-axis, so it's increasing. The derivative is decreasing, so it's going to be concave down. So it's going to do increasing and concave down. Then it's going to switch to, the derivative is switching to negative, so it's going to be decreasing. The derivative is decreasing, so it remains concave down until we get to this point here at negative 2. So at negative 2, we're still, the derivative is going to be below the x-axis, so it's it's a negative derivative, means we're decreasing, but it's going to be an increasing derivative, which means we've changed to concave up until we get to -1. So here now is our relative minimum. So the derivative is changing to positive. So it's going to be increasing now, and the derivative is increasing, so it's still concave up until we get to 0. I think I'm going to move that down a little bit. So let me repair my axis, and I'm going to pick this to go something like right there. Now, once we get to here, we're going to get a corner point, and because the derivative is undefined, and then we're going to switch to decreasing. And the derivative itself is increasing, so we're still going to be concave up. So we're decreasing and concave up until we get to x equals 1. Now we're going to have our relative minimum right here, and it switches to now the derivative is positive, so we're increasing, the derivative is increasing, so we're concave up. So we're increasing and concave up until we get to x equals 2. Now we're going to switch to decreasing, and because this is horizontal, that means we're going to get a straight line that has a slope of -2. And I don't really have markings there, but maybe I'll put some in. So I'm going to call that 1, 2, 3, 4. So if we're going to go a slope of -2, then I'm going to go down 2 over 1 and make that a straight line, something like that. All right, kind of crazy. If we get more, well, there's kind of what they did, which agrees with us. That's good to see. Okay.